And now, the landing of the first ball. Today we will be looking at the conservation of energy. And since I have nothing else to say, let's dive straight into it. Once again, this is Einstein's first law of thermodynamics. It states that energy cannot be created or destroyed, it can only be converted from one form to another or transferred in the form of work and heat. So we've discussed a lot about work in the past few lectures. But now let's consider cases in which the system does not exchange work with the environment, but instead only converts energy from one form to another. More specifically, from between kinetic and potential, since we covered those two. You saw earlier that we had a ball falling through the air. And the energy conversion, conceptually, is pretty easy to understand. At first, the ball, at a high point, the ball would have a lot of potential energy, and as it falls down, the energy conversion, potential energy will decrease and kinetic energy is going to increase. That's the conversion of energy, right? Something like this. Pretty cool, eh? Now let's move beyond the conceptual stuff, which is pretty easy, and try to analyze it with math. Let's say the ball is falling through a displacement of delta D from the positions H, I to H final. At first, the ball is going to have a velocity of VI, velocity initial, and by the time it reaches the bottom, it's going to now have accelerated because of gravity to a velocity F. Now, using a kinematics equation over this period of time, we know that all these variables have the following relationship. Delta D, displacement over here, is just final position minus initial position. Now we rearrange this. So I've also expanded this into here, and then expanded that, multiplied it into here as well. And this acceleration over here, you know this is going to be acceleration due to gravity, so you know the value is 9.81, but I'm not going to write it as the subscript g over here. Okay, next we multiply by the mass on both sides, and divide by 2. Just going to simplify this a little bit. Now I'm going to group these terms. I'm going to put all the initial terms onto one side and all the final terms on the other. So you see something very suspicious over here. Well, this one, isn't that the formula for kinetic energy? And isn't this the formula for potential energy? The same thing over here, right? So let's rewrite it as this. Now this last bit in English, that just means the total kinetic and potential energy initially is equal to the total kinetic and potential energy after the fall. And that's just a mathematical expression of the conservation of energy. Remember that law of thermodynamics that we looked at. The total mechanical energy in the initial state and the total mechanical energy in the final state are the same, are equal. And this principle, of course, can be used in any system where mechanical energy is conserved. And now let's apply this in a problem. Now remember when we looked at this problem of this penguin sliding down a slope, we were looking at forces, and when we looked at forces, we needed to deal with the angle of the slope over here, and then how much force it has, and all these components, and that got really confusing, right? But let's try this question again, this time with energy. So there are 3 simple steps you can take to solve most conservation of energy problems, which are outlined over here, and we're going to go through each of them and do them on this penguin. And of course, just to remind you once again, energy in this case is conserved, so the penguin isn't exchanging energy with the environment, so work equals 0, only energy conversion. The slope is 1 meter high. First, we got to determine the initial and final state. In this case, the initial state is when the penguin is on top of the slope, 1 meter above the ground, and the final state will then be when the penguin has reached the bottom of the slope and traveling at a velocity of v final. Easy enough. Okay, so we've determined the initial and final states. Next, we need to find the known variables in the conservation of energy equation. So I'm going to reproduce that equation over here. So what are our known variables? Well, in the initial state, the penguin has no velocity, right? No velocity means he doesn't have any kinetic energy, so kinetic energy initial will be 0. And in the final state, the penguin now has no potential energy. Of course, seeing that the ground is our reference point. So there's no potential energy relative to the ground. So we're really left with all potential energy in the initial state changing into all kinetic energy in the final state. And now let's write out the formulas for potential energy and kinetic energy. In this case, we can cancel out the mass, and that's true in most of these cases. You find it interestingly enough. And the last step will just be to solve for the unknown variable, which in this case is Vf. We're trying to find Vf here. So it's 9.81 meters per second squared, acceleration due to gravity, and 1 meters, which is the height. That gives us an answer of 4.4 meters per second. Alright, that wraps it up.